Harvey Sykes. He's my final year PhD student, and he's going to tell us all about Citadels.
Thank you. Yeah, thanks for giving me the opportunity to talk. Yeah, what I'm going to talk about today is this general theme in which you might take something like a reductive group and you want to think about it sort of geometrically maybe. And so you construct this sort of simplicial complex out of various subgroups. And you can then transport questions about subgroup structure of your reductive group into questions about this sort of geometric object. And the question is, how much does this extend? How much does this interplay between algebra and geometry extend? And I'll try to convince you that it does, but you have to think a little bit, have to be a little bit more careful. Okay, so I'll just review what we know for reductive groups. This is very much the motivation. So K will be an algebraic closed field. G will be a connected reductive group over K. So the first thing we want to do is we want to fix the maximal torus, T. This somehow rigidifies the structure a bit and you get a root system going on in the background. And you want to then go a bit further and you choose a Borel subgroup, which contains this maximal torus. And this corresponds to choosing sort of a positive system within this root system. So Borel subgroup here, meaning maximal, connected, closed, solvable subgroup. And we've got quite a nice decomposition of reductive groups by their Borel subgroups called the Bruchar decomposition, which is going to appear throughout the talk. So I'll write it down sort of in full. So it sort of comes in two parts. So first, you can decompose your group into a disjoint union of double cosets with respect to this Borel subgroup, where here this W is a Var group, so it's a finite Coxeter group. Okay. And secondly, you can sort of think about, well, how do these double cosets sort of multiply? How do they behave together? And I'll just write this down now, but I won't for the rest of the talk. But if you have two double cosets, so here S is one of the simple reflections in your Coxeter group, then this either becomes sort of a product BWB, BSWB. And this matters less. But what does matter is that this depends very much on whether SW is less than W in what's called the Bruchar order on your Coxeter group. Okay, and then otherwise, yeah, BSWB. Otherwise. Okay, and so the thing that matters, the thing that I'm trying to highlight is that there's some dependency here on the Bruchar order when you're thinking about how these things behave. Okay, and from a Bruchar decomposition, you can define what's known as a W metric. So this really is some kind of distance function. So this is often delta. So this is a function on your coset space, G mod V. And this is W metric, meaning it takes values in the Coxeter group. And so the Bruchar decomposition, the first part sort of tells you that this is well defined as a map. And then the second part tells you that it behaves a bit like a metric. So there are sort of triangle inequalities and things like this going on. And so you say that GB and HB are at a distance of W from each other if G inverse H is in this sort of distinct double coset. Yeah. Okay. And so what do we have? Well, what this is going to eventually give us is, in particular, you have your group, G, is acting on your coset space as a set. So just a set now, but now we can equip it with this W metric, and we call this thing a building. It's a spherical building. Okay. And then you can sort of think about, well, using this action, so an element of the building is called a chamber. This is B and B. And by looking at the stabilizer of the chamber under this action, then you get correspondence between chambers and Borel subgroups. Okay, well, what's the next thing up from a chamber? It's a point. Well, it's sort of like a ball almost. And these are called residues. Okay, so residue R in your building. these will correspond to the so-called parabolic subgroups. So this sort of geometric space somehow encodes all the parabolic subgroups and Borel subgroups, and the way in which the metric behaves on this space is governed by the Brouillard order. So here the residue might look something like this. So it's radius J, where J is a subset of the simple groups. It might be centered at a point B. And these are all the points of your building which are a distance within WJ. Okay, well, that's the parabolic subgroup of your Coxeter. Okay, and so there's this interplay between algebra and geometry, and things like complete reducibility that Adam was talking about can also be rephrased. Obviously, Adam's very interested in parabolic subgroups and how they behave, and you can write it in terms of how certain fixed point subcomplexes behave in a building. This is often lets you get quite nice uniform results in complete reducibility if you're not as enthusiastic about the casework as Adam. Okay, so this is reductive groups, and so why am I trying to extend this? I'm trying to extend this to a class called the Katz-Moody groups. Now I won't define these formally, but I'll sort of try to motivate them. So again, K is an algebraic first field. And where these things come from, how you should think of them is, think about this sort of classical result of Chevrolet, which says that, well, the connected reductive groups over K, these are somehow in sort of correspondence with what's known as root data. These sort of describe how multiplication works in the group, describes the tori. And in particular, these are sort of a datum here. The first thing that you might want to have in the datum is a matrix, which is the thing I care about here. This is a Cartan matrix. And these are the things that classify semi-simple Lie algebras. And there's sort of the observation of Katz and Moody is that you can, first of all, define Cartan matrices axiomatically. And one of these axioms is that they're positive definite. And if you relax this condition, if you relax the fact that A is positive definite, you can still reconstruct the Lie algebra, and now it might be infinite dimensional. And you can also reconstruct an analog of these connected reductive groups. And these are what I'm calling a Katz-Moody group. Define the Katz group. Sort of, by construction, these things behave structurally similar to reductive groups. So what kind of thing? Well, G is generated by a maximal torus and some groups called U alpha, where these alphas are indexed by a kind of root system. So first of all, T really is a maximal torus. It's a finite dimensional algebraic torus. This root system, these are the real roots of a potentially infinite root system. I won't tell you what that means, but there's a root system going on, but now it might be infinite. And these U alphas really are just copies of the additive group. So these are one-dimensional unipotent subgroups. Okay. Now, what's an example? Well, other than obviously the connected reductive groups, you can get things like loop groups coming up. So these are infinite dimensional groups. So sort of pick your favorite connected reductive group and then look at it over the Laurent polynomials. These are called the affine Katz-Moody groups. And you also get lots of weird groups that we don't really have any concrete examples of. But these, we know, are non-linear in the sense that there's no homomorphism into some general linear group over a field. Okay, well, what do we want to do? So we want to construct something that looks a bit like a building. How do we do it in reductive groups? Well, you look at Borel subgroups. And sort of this idea of a Borel subgroup being characterized by being soluble doesn't really work in infinite dimensions. So you go to this characterization of Borel subgroups via positive systems of roots. Okay, and we have a root system, so we can define a positive system of roots. So we'll say a closed subset. And by closed, I mean closed under addition. So a closed subset psi of our root system is a positive system if two things hold. So if psi intersected with its negation is the empty set, and if psi covers the whole root system with its negation. This retrieves back the positive systems in finite root systems. And so from infinite root systems, all of these are determined by a single regular hyperplane in your root system. Whereas now you can get non-standard systems where you first take a hyperplane. This hyperplane contains an infinite root system on it. Then you have to take a successive hyperplane to get another positive system. Okay, so let's split this up. So the first one, let's look at what we know, regular hyperplanes. And the theory behind these is very well known. So you can define a notion of a Borel subgroup, sort of just manually. So you say you have a positive and a negative one, and these are generated by this distinguished torus and half the root groups. You take all the roots in one of these standard partitions, which I'm denoting by delta plus and delta minus. And you also get a Brouillard decomposition. In fact, you get two. So you also have that G is the disjoint union over W, where now W is just a crystallographic Coxeter system, Coxeter group. So it might not be finite. So you B epsilon, W B epsilon, where epsilon is either plus or minus. Okay, and so by the same kind of construction, you define two different buildings now. Because these subgroups might not be conjugate. So you get two buildings, which are B epsilon, and these are the coset spaces, like so. And so maybe I should just give an example of what these Borel subgroups look like. Well, in the loop group, so let's take the simplest loop group, maybe SL2. These things are sort of conjugate to upper triangular mod T, or upper triangular mod T minus. So B plus might be KT. Something like that. Okay. And so we have two buildings, which is nice. But that's not all. And in fact, you have another function, which I'll get on to. Okay, so we've got two buildings. Both of these buildings look like the ones you see in reductive groups. But now you also have a third decomposition called the Birkhoff decomposition. So you can also write your group. And I'll give both parts of this time. Right, B epsilon, W B minus epsilon. So now you're relating the cosets of B epsilon with the cosets of B minus epsilon. And you can also get a similar kind of multiplication between these cosets. So I won't write down the full thing, but you get the analogous multiplication. Except from now, rather than depending on the Brouillard order, you reverse the order. So you sort of depend on the reverse Brouillard order, as it were. Okay. And so what we have is we have two buildings, and now we have some kind of co-distance between the buildings. And this co-distance, rather than being governed by the Brouillard order, is now given by the reverse Brouillard order. So B plus, B minus, form what's known as a twin building. The type WS. Okay. This is cool. And you could stop there. You can define a notion of complete reducibility using this, and Crass and Dawson have studied these kinds of complete reducibility, but I've just sort of propped up the talk by saying that actually these non-standard systems of roots. So be ashamed just to stop here, right? So let's look at what the non-standard ones give us, and this is where the work on my thesis comes in. Okay, and so to introduce non-standard systems, we need to bring in some machinery of Dyer in the 90s, who says that to every positive system, you can define two things that we're going to need, two ingredients to define one of these structures. You can define, first of all, a kind of order on your Coxeter group, so a twisted Bruchau order. And you can also define a reflection subgroup. And the way you should think about this is you have a positive system. You want to think about the groups that are sort of simple with respect to the system. Then you look at the groups generated by the corresponding reflections. So what do these orders and reflection subgroups look like? Well, let's sort of bring it down to earth by looking at the standard systems. So if psi is just our standard positive system, then as you might hope, the twisted Bruchau order is just the Bruchau order. You retrieve it back. And the reflection subgroup is just the whole Coxeter group. Okay, well, great, that tells us about our first building, but what about a twin building when you introduce the negative system? So what psi is the negative one? Well, now the Bruchau, the twisted order, is now the reverse Bruchau order. And you might be able to start seeing the pattern there. And the reflection system is just the whole group. Okay, and so you might be able to sort of start guessing, well, what are these non-standard systems going to look like? How are we going to build them? In general, they can get quite weird. So this twisted Bruchau order somehow sits between these two orders. So it really can be different from both of them. And this reflection subgroup is often a proper subgroup. And it can be trivial. Nice. Okay. So in the same way as people do in the literature for the Borel subgroups, let's define some analogues of Borel subgroups using these non-standard systems, and these are going to be called quasi-Borel subgroups. And you define them exactly how people have defined their standard ones, except for now I'm going to introduce this identity component part, but I'm not going to go into why that's there. This is just generated by T, and the U alphas coming from your positive system. Okay. And this is a result of Billig and Dyer, again from the 90s, who sort of partially prove a Bruchau decomposition using these weird Borel subgroups. So what do? So they say G is the disjoint union of B plus Q psi, like this. So there is a W-valued map now between these two coset spaces. And how does it behave with respect to multiplication? Well, they only do the left multiplication. So what do? So BW Q psi. E plus S Q psi. And this, you get the analogous things that, so from now, rather than depending on the reverse Bruchau order, you plug in these twisted orders. So if SW is less than in the twisted Bruchau order. Okay. And the problem is that this is kind of symmetric. This describes both left and right multiplication, whereas this doesn't. It only describes left multiplication. And so this is my first small contribution, is proving the right multiplication. Okay. So as you might imagine, there is a right multiplication proposition 2. This looks like so. Like this. And it behaves exactly as you might expect. So from now on, you need to multiply from the right. And notice I've changed from S to T here, because now this is a simple reflection of sort of simple reflections of this proper reflection subgroup. We do need to be a bit careful then. Okay, and now with my remaining time, I'll just bridge this all together and show what kind of structure you get. So what do we have? So the naive object that you might want to study is the coset space of G over these quasi-Borels. But actually, that's not quite what you get. And it's not quite what you get because sometimes this reflection subgroup is proper. And so actually what you get is G over Q. And now I have got rid of the identity component, but don't worry about that. There's a family of buildings. So it's a disjoint union of buildings, which I'll write as B psi I, so indexed by I. And these are all, rather than being type WS, these are type W psi S psi. Okay. And also, what does this Billig-Dyer decomposition tell us? Well, it tells us that there's a map between these buildings to the standard building. There's always one of those. So how might we write this? Well, B plus, and any one of these non-standard buildings form a generalization of a twin building, which I've called a twisted building. Okay. And you can prove that these twisted buildings behave quite similar to twin buildings, and they support things like projections, and they have a notion of convexity, if you're familiar with buildings. And so what we have is we've now encoded all of these twisted Brouillard orders in an object. And so we might as well bring them all together into one cohesive object now, which is called the Citadel. Okay, so the Citadel, so this is an object on which a Kac-Moody group acts, G, and you can define this completely axiomatically, is this space, CG, the disjoint union over all the orbits of positive systems of these sort of coset spaces. Okay. And what does this sort of schematically, what does this look like? Well, you have your standard building in the center. This is the one that currently appears in the literature. But we want to think about all these other non-standard ones. And so in type A2 tilde, there are 3 others. So you might have there also indexed by the simple roots of the underlying A2 root system. So you might write these as so. And what we've shown that, well, the central building always has a distance function, a twisted distance function to any of these outer buildings. So somehow looks like this. And each one of these encodes these strange twisted orders. And this is sort of the imagery that you should think about for a citadel. And I think I'll leave it there. Thank you very much.
Do you have any questions for Harvey? I do, but it's not fair. Okay, so you've got this gigantic object that generalizes just the spherical building of a reductive group. How much of the general theory of buildings and complete reducibility does it bring with it?
A lot, basically. So these you can think of the Citadel as being sort of a disjoint union of all these. And so locally, you sort of think of them as these twisted buildings here. And these have notions of projection, notion of convexity. So you can define complete reducibility using Citadel. And you can get these results, some of the results that I haven't talked about sort of Levy subgroups having this hereditary property. You can sort of get quite quickly some results in this direction using the Citadel, which you don't see using the twin building. So this introduces a whole load of different subgroups, these quasi-parabolic subgroups that can feed into a definition of G-complete reducibility.
Any more questions from the audience?
How do these quasi-parabolic look, for example, in SL2?
Yeah, well, in SL2 they're not as interesting. I mean, just because it's not big enough, but I can show you. So maybe I should. So in SL, I'll do SL3 just because it's a bit more obvious what's going on. So your central Borel subgroup is upper triangular mod T. And then this guy up here is the upper triangular matrices. Okay, this is a non-standard system of roots in an infinite root system. It's quite strange. And then down here, so this relates to your alpha of your underlying SL3. And so you have a standard Borel up at the top. And then you have sort of quite a strange uniform radical. Right. So this is why. So these buildings here type A1 tilde. So you should really think of them as the A1 tilde sitting right here. And then you have this. So what's going on is you're taking a hyperplane and that's giving you the block up a triangular. And then your second hyperplane is then cutting it up into a standard Borel subgroup. And then, yeah, the bottom one is a big A1 tilde down there.
Right. Any more questions? If not, let's thank Harvey again.